In this video, I'm going to go into more detail regarding the feral tissue model, specifically the 6 programs that we want to turn off and the protocols you can consider to do that. First, take a look at the logo on the right side of the screen. The logo is a map. It shows how healthy cells become feral and how we might help these lost and confused cells find their way back to good health. I suggest you take a moment to click on the logo at feraltissue.com. It will bring up a copy of this map that you can print out so you can follow along. I'll leave the map up on the screen so that if you can't print it out, you can see it as we take this journey together. Okay, first, if you're dealing with feral tissue now, take a slow breath. This is your map and I will be your guide. We begin at the bottom of the map where it says good health. This is where we were before cells started misbehaving and becoming feral, and this is where we want to return to. There are 3 colored circles in the center of the map. They represent the 3 primary triggers for feral tissue behavior. There are also 6 terms around the outside of the logo. They represent the 6 programs that these 3 primary triggers activate. Our goal is to remove the 3 triggers and turn off the 6 programs and return to good health. Above the term good health is a brown circle that says SCFA. SCFA stands for short-chain fatty acids, and the brown color is the color of our stool. It is a reminder that we want our microbiome in our large intestine to be healthy and making good short-chain fatty acids for us. If you are unfamiliar with what short-chain fatty acids do, you may wish to watch our videos on the microbiome. Unfortunately, due to antibiotics, pesticides, chlorinated water, and other toxins, many of us do not make enough good short-chain fatty acids. This is the first primary trigger, a lack of short-chain fatty acids. This deficiency leads to the first of 6 programs that we will want to turn off, and that is receptor upregulation. Let us say a fisherman needs to catch 5 fish a day to feed his family. One day he catches only 1 fish, the same the next day and the day afterwards. He jumps in the water and looks around and sees there are a lot less fish than there used to be. So the following day he brings 5 fishing rods with him. Now he is able to get more fish. This is an analogy of what happens in the body. Every cell has little fishing rods on their membranes to bring in needed supplies. We call these receptors. When there isn't enough of a needed substance, the cell simply puts out more fishing rods. In the body, we call these receptors. So, if our microbiome doesn't make enough short-chain fatty acids, then cells increase the number of receptors that can bring short-chain fatty acids in to the cell. The receptors for short-chain fatty acids are called AHR receptors, and you can see them inside the indigo-colored circle with the letters AHR inside. This is how the first program gets turned on. Not enough short-chain fatty acids from a microbiome, and this gives us the increase in the AHR receptors. This has an unintended consequence. The AHR receptors are what are called promiscuous receptors. That means that there are a lot of things that can bind to them. A chemical that binds to a receptor is called a ligand. There are hundreds of ligands that can bind to the AHR receptor, and most of them are not good for us. The connection between toxic ligands of the AHR hydrocarbon receptors and feral tissue is well documented in the scientific literature. One famous toxic ligand is dioxin, the toxic chemical in Agent Orange. Another issue is that certain fungi, bacteria, viruses, and parasites have learned how to make ligands that can bind to our AHR receptors as well. Why would they do this? AHR receptors deliver the ligands right to the DNA. When the ligands are good short-chain fatty acids, our DNA is properly regulated. Certain infections, however, hijack the AHR receptors with their ligands and trick the DNA into suppressing the immune system. This lets infections live in our body without our immune system attacking them. Nearly 20% of all feral tissue is associated with viruses, including Epstein-Barr and cytomegalovirus, two common members of the herpes family of viruses. This is likely due to the ability of the herpes-type viruses to damage the critical p53 gene, which triggers the self-destruct apoptosis signal in dangerously growing cells. Without this important gene functioning properly, damaged cells can replicate without limit. Aflatoxins from fungi and mold are also known to cause feral tissue. Even some parasites are correlated with feral tissue. So, what can we do about this? First, consider increasing your short-chain fatty acid levels so that the AHR receptors don't increase in numbers and actually go down to their proper quantity. It was a low short-chain fatty acid level that turned on the receptor upregulation program, and it is healthy short-chain fatty acid levels that may be able to turn it off again. In the short term, consider a short-chain fatty acid microenema such as Filamet. For the long term, you could consider our Pokageshi powder and Panaceum. Since Filamet is acidic and we want to alkalinize the tissue, more on this shortly, Filamet should always be done with an alkalizing agent. You can consider our bicarbonate product. Second, consider cleaning toxic ligands off the receptors and blocking them from reattaching. Indigo naturalis plant extract is one possible choice for this, and you could consider our Receptor product. Indigo extract has been shown to be 45 times stronger at binding to the AHR receptor than dioxin, which is the toxic ligand with the most binding power ever discovered. Dioxin is such a strong toxic ligand that it has a 5-day half-life on the AHR receptor and a 7-year half-life in the body. If indigo extract can displace dioxin, it should be able to displace any other toxic ligand as well. Third, consider removing toxic ligands from the body. You could consider our Zenaplex product. Fourth, consider supporting the body in dealing with viral, fungal, and parasitic infections, as well as supporting the p53 apoptosis gene. You could consider our Allergica product. While for some people, increasing the AHR receptors is enough to get their cells the short-chain fatty acids they need, like the fisherman and his 5 fishing rods. For others, even receptor upregulation is not enough, and this brings us to the next program, fermentation. Okay, not enough short-chain fatty acids, but the body really needs them. Well, the next program it runs I call the fermentation program. This is where the body alters some cells in such a way as to have them produce short-chain fatty acids. It has been said that feral cells are cells that ferment. Usually fermentation happens in a low oxygen environment, but in feral tissue, it can happen in the presence of oxygen. This is referred to as the Warburg effect. This is where sugar isn't burned in the Krebs cycle for energy, but fermented into lactic acid, a short-chain fatty acid, instead. This is an emergency program. It is not meant to run continually, but unless the microbiome is fixed, it will keep running. I should mention here that while the fermentation pathway creates lactic acid, there is another pathway that feral tissue can take, and that is into the Krebs cycle, but backwards. It's called the reverse Krebs cycle. This is an unnatural way for the cell to operate, and it's not surprising that there are 3 places in this cycle where it is difficult to go backwards. To get past these 3 difficult spots in the reverse Krebs cycle requires a substance called ferredoxin, which is an iron-containing compound. As such, consider chelation to lower iron levels and thus lower ferredoxin. To this end, you may wish to consider our metacardium product. Back to fermentation. Since fermentation is less efficient at generating energy than normal cellular processes, it has to run up to 100 times faster than normal cell cycles. This leads to the creation of an enormous amount of acid, as each cycle of the fermentation process not only generates lactic acid, but also 2 hydrogen protons, which are themselves acidic. Other than lactic acid, which is also produced in the muscles during anaerobic exercise, short-chain fatty acids are only supposed to be produced in the large intestine. The colon is specifically designed to handle these acids and deliver them into the bloodstream slowly, but when the fermentation program runs, and the short-chain fatty acids, as well as the acidic hydrogen protons get created in other parts of the body, these acids build up and cause acid burns. To deal with the acid burns, the body tries to repair the injury. This takes us to the 3rd program, the stem cell program. Moving clockwise around the outside of the circle, we now come to the stem cell program. When tissue is injured, it is stem cells that do much of the repair. Stem cells are those cells that have not differentiated into any particular kind of tissue. They can become anything: a heart cell, a nerve cell, a pancreatic cell. Our bodies try to keep an equilibrium of stem cells and normal or differentiated cells, a certain ratio of them. To do this, when we are injured, our body turns normal, differentiated cells into undifferentiated or dedifferentiated stem cells so that they can repair the injury. This is all well and good in normal injuries, but with chronic injuries, this can backfire. As the short-chain fatty acids build up, the area becomes more and more acidic, injuring the cells and the tissue. These acids, however, aren't the only things causing injury. Let's go back for a moment to the first program, receptor upregulation. This program increases the AHR receptors to try to bring in more short-chain fatty acids. But as mentioned, this program has a weakness. AHR receptors don't just bring in short-chain fatty acids, they also bring in viral, fungal, bacterial, parasitic, and chemical toxic ligands. So in addition to the acidic environment, infection metabolites and toxic chemicals may also be injuring the cells. To deal with all this injury, normal cells are turned into stem cells, but they cannot deal with the cause of the injury, the acids, infections, and toxins. So more and more cells are triggered to become stem cells. This is one of the hallmarks of feral tissue, normal cells dedifferentiating into stem-like cells. Indeed, the number of stem-like cells and the degree to which they have dedifferentiated is used by pathologists to stage and determine just how dangerous a feral tissue sample is. As more acids and toxins build up, the cells activate the next program, the mucin program. There is a program that the intestines, lungs, and sinuses have in response to acids, toxins, and irritants. I call it the mucin program. It is the secretion of mucus, which both protects the tissue as well as traps and removes the toxins. In the lungs, tiny hair-like cells called cilia move pollutants and irritants trapped in the mucus out of the lungs. In the intestines, continual shedding of the intestinal layer into the stool also keeps mucus fresh and renewed. Feral tissue, however, has no cilia or shedding that can remove the mucus that is formed. Instead, it just sits there, becoming a biofilm home for chronic infections and decreasing the absorption of any supplements or drugs we may take to try to deal with the feral tissue. As the acids continue to build up, the cells move into their next program, the sloughing program. There is only one place in the body where short-chain fatty acids are supposed to accumulate, and that is in the large intestine. To deal with the acidity from short-chain fatty acid production, cells of the large intestine are sloughed off every few days into the stool. This prevents the large intestine cells from becoming feral due to a continual exposure to an acidic environment. Unfortunately, this sloughing program also happens in feral tissue. In feral tissue, the acidity causes a decrease in the adhesion molecules that hold cells together, so they can float freely. The acidity also triggers the production of high levels of enzymes such as collagenase, gelatinase, hyaluronidase, laminase, and cathispin. Adhesion molecules are what keep cell types together. Liver cells stick with liver cells, heart cells stick with heart cells. We don't want our liver dissolving into independent cells and floating through our body. This is the job of adhesion molecules. Unfortunately, these enzymes break down the adhesion molecules and dissolve the surrounding tissue, which allows free-floating feral cells to get into the bloodstream. Unfortunately, in feral tissue, the sloughing program triggers cells to break away from other cells like themselves, and the enzymes dissolve the surrounding tissue, which allows these free-floating feral cells to get into the bloodstream and lymphatic vessels, where they can create outposts in distant parts of the body. What was a great and protective program in the large intestine becomes a very dangerous program in feral tissue. This leads us to the last program, the trophoblast program. But before we talk about trophoblasts, let's talk a little bit about pH. The circle with the green color with the letters pH represents the acid-alkaline balance of the body. The color is dark green because that is the color you want your pH paper to be when you test your urine and saliva. A 6.8 urine pH and saliva pH are optimal. However, initially in this protocol, you should consider getting your urine pH to 7.5 or 8.0, at least until the feral tissue issue has been resolved. You can test your pH with pH paper that goes from 5.5 to 8. Optimally, you can get a portable digital pH meter like the Lacroix Twin, shown here. Something very odd happens to the pH of feral cells. Internally, they become very alkaline, and externally, they become very acidic. How does this happen? The model I am proposing states that feral tissue is making short-chain fatty acids due to a lack of short-chain fatty acid production in the large intestine. Okay, these short-chain fatty acids now have to get out of the feral tissue cells and into the general circulation. There are two ways they can do this. They can be exchanged for bicarbonate, and they can be exchanged for sodium. That means that when the short-chain fatty acids leave the cell, either bicarbonate or sodium have to take their place. Since bicarbonate and sodium are both alkaline, this causes the cell to go alkaline on the inside. Since short-chain fatty acids are acidic, this brings acids to the outside of the cell, and it becomes even more acidic since the alkaline elements of bicarbonate and sodium were removed from the extracellular environment. And this is exactly what we see. Feral cells are alkaline on the inside and acidic on the outside. And since alkaline bicarbonate will not pass by diffusion out of the cell but only by an active pump, the bicarbonate just keeps building up inside the cell, making it more and more alkaline over time. This process is called a reverse pH gradient. Alkaline on the inside, acidic on the outside. But wait, you might be thinking, isn't alkalinity good? No, not like this it isn't. An excessively alkaline environment supports fermentation, the second program, but at a terrible cost. It is this alkalinity inside the feral cell that drives most of its unwanted behavior, including rapid growth. Alkalinity also damages the lysosomes. Lysosomes are small organelles in the cells which are responsible for degrading or storing toxins, such as the toxic ligands that excess AHR receptors can bring in, as well as participating in apoptosis, which is the program that causes dangerous cells to self-destruct. For those that choose a standard treatment model, as little as a 0.4 increase in intracellular pH towards the alkaline has demonstrated a 2,000-fold increase in resistance to doxorubicin, a chemotherapy drug. On the other hand, it is the acidity outside the cells that drives invasion and growths at remote locations. So pH is very important. Fortunately, it is not that difficult to shift. The first step is to eat alkaline-forming foods. All animal products, grains other than oats and quinoa, and beans other than lentils are acid-forming. All vegetables other than tomatoes and spinach, and all fruit other than pomegranates, figs, dates, and plums are alkaline-forming. A pH-neutral diet would be 80% vegetable and fruit, with most of it being vegetable, and the remainder being acid-forming foods. Those animal products we eat should be grass-fed beef, pasture-raised poultry and eggs, and wild-caught fish. Otherwise, they too are fed grains, so they become doubly acid-forming. However, changing diet is not enough. Once a person discovers they have feral tissue, they have years, if not decades, of acids stored in their connective tissue to get rid of. So here are some more powerful protocols to consider. One option is to drink 48 ounces of fresh vegetable juice a day. A mix could be half carrot, a quarter cucumber, a quarter celery, and remember, no tomatoes as they are acidic. Another option would be to take hot baths with 2 cups of aluminum-free baking soda every night. But the easiest way to shift pH to the alkaline is to take oral bicarbonates, but it has to be done properly. Just mixing baking soda in water will shift the pH, but it will also wipe out stomach acid, which damages digestion. As such, we make a bicarbonate product that will only open up in the small intestines. It is called bicarbomet. We make a video on it that you may also wish to watch. If you can't get our bicarbonate, then consider 1/2 a teaspoon of sodium bicarbonate and 1/2 a teaspoon of potassium bicarbonate mixed in water that you can drink over the course of the day. Of course, high levels of sodium and potassium should only be taken under the supervision of your healthcare practitioner, especially if you have kidney issues. Finally, some could consider the injection subcutaneously of a 4.8 solution of sodium bicarbonate. If you're going to do that with a syringe pump on the slowest setting, again, this is something that should only be done with medical oversight. pH is very important. Remember, it is the alkalinity inside the cell and the acidity outside the cell that drives most of the behaviors of the feral tissue that we want to stop. We can deal with these pH abnormalities, this reversed pH gradient, by stopping the fermentation program that is creating the acidity and supplemental bicarbonates to help neutralize the acidity that has already accumulated in the connective tissue. We are now at the final stage, the one I call the trophoblast program. The trophoblast is the outer layer of cells of the early embryo. The trophoblast is what becomes the placenta in pregnancy. We could call this the placenta program, but for accuracy, I use the term trophoblast. The trophoblast has a lot of similarities to feral tissue. Both grow very quickly. Both exist in an environment of low oxygen and high carbon dioxide. Both have accelerated blood vessel growth. Both show a lack of contact inhibition, that is, they don't stop growing when they bump into their neighbors. Both have limited Krebs cycle activity and make lactic acid. Both create the pregnancy hormone HCG, which then triggers progesterone, which stimulates migration and invasive behavior. Both produce enzymes that allow them to invade other tissue, and in the case of the placenta, it invades or attaches to the uterus, so it can have an anchor. Both have low voltage. Okay, what about oxygen? You could consider mild exercise while breathing in oxygen. This is called EWOT, or exercise with oxygen therapy. What about low voltage? Low voltage causes a loss of contact inhibition between cells. Normally, when cells touch, they stop growing. This is called contact inhibition. This is how a cut on the skin heals. When the edges meet, little voltage-sensitive receptors called gap junctions in the cells connect and tell the cells to stop growing. Feral tissue cells have less gap junctions, so they are less able to communicate, and almost no voltage, so even if the gap junctions do touch, there's not enough voltage there to tell them to stop growing. Voltage is so important that researchers have found that if you raise the voltage of feral cells, they stop acting feral as long as the voltage is applied. Walking barefoot on the beach or on unsprayed grass is one way, but this may not be something you can do every day. So, you may want to consider using negative voltage electron devices like our portable electron chargers. Okay, if trophoblasts or the placenta is so much like feral tissue, why doesn't it kill every pregnant woman? This is because at about day 56, the fetus starts producing the pancreatic digestive enzyme precursors, trypsinogen and chymotrypsinogen. Why would a fetus do this? It's getting all its food pre-digested through the umbilical cord. It turns out that these enzymes turn off the trophoblast program. It is the trigger that tells the trophoblast, okay, you can stop growing quickly and being invasive now. Mission accomplished. Now just act like normal tissue. Can we use these same enzymes to convince feral tissue to act normally also? Some doctors think so. Enzyme therapy for feral tissue was first proposed by Dr. Beard, followed up by Dr. Kelly, and then the late Dr. Gonzalez, who was its most recent champion. Indeed, studies have shown that the precursor enzymes, trypsinogen and chymotrypsinogen, support the redifferentiation of stem cells back to normal cells. These enzymes are so powerful that feral tissue introduced into a developing embryo can actually turn into normal tissue again. So how might we use these precursor enzymes ourselves? These enzymes come in two forms. The active forms, trypsin and chymotrypsin, and the precursor or unactivated forms, trypsinogen and chymotrypsinogen. What happens is that the enzyme cathepsin found in feral tissues, as a result of the sloughing program, activates these two enzymes, which means they only become active at the site of feral tissue. This is good news. You can, of course, try regular pancreatic enzymes, but these are usually the active form, so they can irritate any tissue they contact. These enzymes can break down elastin in the walls of the arteries and veins and age our circulatory system. What we want are the precursor forms. You could use the precursor forms found in pancreatic extracts, but if you swallow them, the enzyme enterokinase in the small intestine will activate trypsinogen, which in turn will activate chymotrypsinogen, so that's not optimal. To make up for this, practitioners that promote pancreatic enzymes usually suggest 150 to 200 capsules a day. I suspect that these very high doses are required partially because the enzymes are not being delivered in their precursor form. In their precursor form, I believe much smaller amounts would be sufficient. As such, you may wish to consider our Pancremet liposomal enzyme product, which contains trypsinogen and chymotrypsinogen, which are the inactive forms of the enzymes. Since Pancremet is a liposomal product, the enzymes will not get activated in the digestive tract. To conclude, let us summarize. Looking at the map, the 3 colored circles are the main triggers for the 6 programs around the outside of the map. The first trigger is a short-chain fatty acid deficiency, and it is what I believe sets the entire process in motion. It leads to an increase in AHR receptors, which increases the intracellular delivery of toxic ligands, which poisons the cells, suppresses immunity, and causes the genetic damage that other people believe causes feral tissue, but what I believe is the result of feral tissue. This causes a pH inversion, where the inside of the cells become alkaline and the outside of the cells become acidic. This pH causes unchecked growth and dedifferentiation within the cell, as well as invasive behavior outside the cell. Remember, no feral tissue grows any faster than a placenta. No feral tissue is any more invasive than a white blood cell. Deal with the triggers and the programs, and you may find yourself on the receiving end of a miracle. If you have any questions, feel free to contact us at www.feraltissue.com. Take care.